Today I'm going to cover a famous security tool. It's called NMAP. If you've watched a computer hacking scene in any of the Hollywood movies in the 21st century, chances are it's featured a little bit of NMAP action. The Matrix Reloaded, Ocean's 8, Snowden, Dread, Elysium, The Bourne Ultimatum, Die Hard 4, the list goes on. If NMAP is good enough for Bruce Willis, Matt Damon, and even bloomin' Rihanna, then it's gotta be good, right?
Wait, every time you move it, they have to start from scratch.
What'd you do? I turn it on.
Oh.
NMAP is an open source tool that's been going around since as far back as 1999, and it stands for Network Mapper, simply enough. It's an essential tool in the arsenal of a security analyst, so if you don't know much about it, or if you're just starting out in security, then this is going to be a good video for you. So, before I get rolling though, the obligatory disclaimer needs to be made. Whilst using NMAP itself is not illegal, scanning the ports of network systems which you do not have the express permission of is illegal in some countries, and like all security tools, you can use them for good, legitimate purposes, and you can also use them well for not so legitimate purposes. I cannot be held responsible myself in any way for your own actions, so make sure you're a good kid, okay? Now, I'm also going to go through some of the network fundamentals, just in case you aren't fully up on those first. I'm doing that because I reckon they really help with understanding the full power of NMAP. If you know already all of these fundamentals, like if you're in a CCNA or you just have a generally good understanding of networking throughout all the network layers, then feel free to skip ahead the first section of this video. Section 1. What are ports? So before I dive into NMAP, it's important that you understand the concept of ports. If you already know about TCP ports, then as I said, you can skip ahead to the next section of this video, but I'll try and keep it as brief as I can. Read up on TCP IP if you need more information. Suffice it to say, the internet and the majority of modern local area networks utilize two main protocols, of which the rest of the protocols of the internet sit upon. If you are familiar with the 7-layer OSI model, then you'll know that things like cables and MAC addresses are at layers 1 and 2 respectively. The network layer, or layer 3, introduces the Internet Protocol, or IP as we know it. This layer allows the routing of network data, known as packets, over networks, or internetworks. It also has a few other protocols, including ICMP, which is used for ping, amongst a few other things. Next we get to the 4th layer, which is known as the transport layer, and this is where networks and software start to mesh. The TCP and UDP protocols are introduced at this layer, and it is the combination of TCP and often UDP with IP that we often associate services of the internet, thus the popular moniker TCP/IP. The following two layers, session and presentation, deal with things like sockets, SSL, and so forth, but most of the real business of the net happens at the top layer, the application layer. For example, HTTP, the protocol of the web. So when you browse the web, here's what happens. At application layer 7, you browse the website in your web browser. You know what that's all about. At the presentation layer, that's layer 6, any decryption of encrypted traffic, e.g. that's HTTPS, SSL, is handled. At the session layer, layer 5, a socket connection is being established via TCP port 443, or for insecure HTTP traffic, that's port 80. More sockets are opened and closed during different high port numbers depending on the needs of the web browser session. More on sockets in just a minute. At transport layer, that's layer number 4, the socket connection is made from your PC, the client, to the server providing the website on the internet using the TCP protocol. Then down at network layer, that's layer 3, the IP protocol decides which paths over the internet the data needs to be sent and received. The data link layer, layer 2, is where the data is sent through the physical network hardware, Each network card, be it a wired Ethernet adapter or a Wi-Fi adapter, has a unique physical MAC address, media access control address, and these are burned into the hardware at the factory and are unique. This is how packets are switched or routed across networks. And of course, at the physical layer, that's layer 1, the web traffic data is sent across your network Ethernet cables as electrical pulses, on or off. So it's all about the cables and so forth. So you can see how the flow down effect, that's just an example there of how a typical web session happens, but it's the flow down effect here in this example of a web page is requested and transmitted through each of the layers of the OSI model. At layers 4 and 5, data is transferred by what are known as sockets between your PC, referred to as the client, and the server. Sockets are temporal in nature, and they're established only for the duration that they are required by the process on the server. A socket address contains a combination of 3 main pieces of information: the transport protocol, the IP address, and the port number. So our website request socket looks like this. Transport protocol in our example is TCP because the web, HTTP or HTTPS, runs over TCP. However, if the request is something else, for example, a hostname lookup with DNS, it might use UDP. Next, the IP address would include the source and destination IP addresses. The source IP is you, the client. It would likely be the external facing IP address of your router as opposed to your PC, and the destination IP address of the web server. Finally, the port number would be initially either 443 for HTTPS or port 80 for the non-encrypted version of HTTP. All servers sit in a TCP state called listen, and its purpose of this is to listen for TCP socket connections on a given port. When you know that HTTPS usually listens on port 443, it's easy enough just to find out if a particular IP address or hostname is serving web pages. Just point your web browser at it. But what about web servers that are either not listening on the default port of 443 or 80, or what about other services like email and DNS, for example? There are literally thousands of TCP services that could be running on a server. Without running some sort of scanner, it would be very slow, difficult, and tedious to find out if a port is open and listening on a server or not. In effect, you'd have to do something like use the telnet command to connect to the destination server with each port number you wanted to check is listening. This is where NMAP comes in. At its most basic, NMAP automates the process of scanning for ports. Ports can also be in different states than just listening, and NMAP can help with that too. Moreover, NMAP can automate not just the scanning of ports on a single server, but whole IP address ranges as well as whole ranges of other handy things. So, for example, imagine a hacker finds out that a vulnerable version of a service called, let's say, for example, vulnid runs on port 1337. A hacker could run NMAP on a range of IP addresses and scan for just port 1337 across all of those hosts. Or they could just simply run a scan for all open ports on a range of IP addresses too. Obviously though, that would take a lot longer. It's important to note that whilst most internet services run on TCP, there are a number of simple services that run in UDP, and some, like DNS, use both TCP and UDP, so bear that in mind. It's also worthwhile to know that port numbers range from 1 through to 65,535. The first 1,024 ports are known as what's called privileged ports. These ports are pretty much all allocated to more famous services such as port 80 and 443 for the web, 25 for email, and so forth. So these are reserved. They cannot be bound to a socket set to listen, that is, unless you are the administrative user or root of the server. I'm also going to introduce a few other topics throughout this video, including a bit about how TCP handshakes work, because it's pertinent to the different type of scans that you should make with NMAP. Choosing which type of scan to make can help you with host discovery quite a lot, but I promise not to bore you with the theory. Section 2. Getting and installing NMAP. NMAP is a freely available tool. If you run Linux, it's quite possibly available in your distribution's extras repositories. So if you're using something like Debian or Ubuntu, a simple sudo apt install nmap should suffice to get you installed. Similarly, for Red Hat based systems, either sudo dnf install nmap or sudo yum install nmap will also do the job. Whilst there are a few graphical clients for nmap out there, they are just generally loose front ends for the command line tool. And if you're an aspiring pen tester, you never know when you'll be a machine in the field or SSH'd into some box in Bumsville, Idaho that you don't have access to a graphical desktop on. So I'll be teaching you to use the CLI or command line interface tool only on this tutorial. If you run Mac OS or Windows, then you can download the binary installers from nmap.org's website, and if you want the easy installation route, then you should also be able to get nmap through Brew, Think or Mac ports on macOS, if you use any of them. With the Windows installation, you may also need to separately install the Windows npcat binary. Once you have installed it, running nmap should be run as root on a Unix system or administrator on Windows. Running in Linux or macOS will probably involve using sudo to temporarily become the root user. It is possible to use nmap in its most basic form as the non-root user, but any stealthy capabilities are not available. Section 3. Using nmap. The most basic usage of nmap is pretty straightforward. All you need is the IP address of the target server that you want to scan. For example, you can scan your own machine's ports just simply by typing nmap localhost. You'll probably get a response that looks somewhat like this. Starting nmap at the time it started, and then looking for ports not shown, 997 closed ports, and then it shows 2 ports in my machine here that are open. Port 22, which is SSH, and port 631, which is the internet printing process. I think that's what it stands for anyway. Now, you might have already been thinking about this, or not, but now is probably a good time to have a quick word on firewalls. Say I had a firewall in front of my local host machine here. Let's just call this one computer A. And now I was scanning from a computer that was behind that firewall. Let's say computer B. So computer A, firewall, and then computer B where I'm running nmap from. Okay, so assuming that I hadn't configured the firewall to pass through traffic to computer A on the firewall, then you wouldn't be able to see those ports as being open. Running nmap on computer B against computer A would show no open ports, even though the ports are open and listening on computer A, they are being blocked by the firewall. Nmap really comes into its own when you use it to do laborious things, like scan ranges of ports or ranges of servers. So here's an example of how to scan a range of servers. Nmap 192.168.1.1-254. I think you can easily figure out that that scans every IP address in the range of 192.168.1.1 all the way through to 192.168.1.254. You could even use a text file that contains a bunch of IPs. Just use the -il textfile.txt option. You can exclude hosts too. So if you have a range of 254 hosts and don't want to scan 192.168.1.200, just tack on -- exclude 192.168.1.200. By the way, if you're enjoying this video so far, I'd really appreciate it if you pause it for a second, press that thumbs up button, press subscribe, and then set the notification bell to alert you when my videos come out. That way, I'll get a good indication I'm making good content, and I'll keep on making more. It takes many hours to do the editing, research, and scripting of my videos, as with any decent content creator, so if you feel like helping the cause, please consider pressing the join button beside my subscribe button here, and this also gives you exclusive early access to the videos and some members only content, including getting your name on the credits. I am also on Patreon, patreon.com/alsgeeklab. Okay, on to section 4, host discovery. So before we delve into port scanning techniques, it's also worthwhile knowing that Nmap is great at reconnaissance to find out if there are active hosts on a given IP range or subnet. In fact, some people just use Nmap to figure out if they have rogue machines on their network or have machines statically set in a dynamic IP pool. So let's just say that I want to see what hosts are on my home network. These hosts have to be switched on and their network interface is in the up or online state. I can do sudo nmap-sn 192.168.1.1/24. This will scan the network in host discovery mode. It means that it won't start connecting to the ports. I've used the subnet/24 notation, but you can also write it as 192.168.1.1-254. In this case, it would have the same effect. If I execute that command as root, Nmap will try and obtain a fingerprint as well for each of the hosts, and it's usually pretty accurate. For example, my scan showed that up at 192.168.1.67, a Google device, which happens to be my Chromecast, and then at 192.168.1.71, it showed up a Raspberry Pi trading. Yep, you guessed it, that's a Raspberry Pi. So this is super handy if you don't know what IP address a particular device might be. Running the scan as root took 5.01 seconds. Running the same scan as a non-root user took nearly 70 seconds more. So if possible, do it as root. Talking about the timing, you can do the -n flag to never do DNS resolution. Looking up domain names, especially if the domains are on the internet or if there are DNS timeouts at play, they can take a lot of time. So you can use this flag to never use DNS lookups. However, do bear in mind that sometimes host names, especially when reverse lookups are involved, can be quite revealing, quite helpful in recon. So if you're following along, why don't you pause this video and run the discovery probe on your own network for a second. You might be surprised to find devices that you either forgot about or are rogue devices. So sudo nmap-sn and then your IP address network. Nmap also allows you to use ARP for discovery. ARP stands for Address Resolution Protocol. Think of ARP as the DNS service for IP addresses. It maps the unique hardware address, MAC address, of the network adapter to the IP address at which it is bound. So you could run sudo nmap 192.168.1.1-254 -PR -lowercase sn. This would give you the MAC address and hardware vendor ID, e.g. Apple or Google, etc., for all of the devices on your network, as well as their IP addresses. It's a very effective and quick way to probe the local area network, especially if you only need to scan the same subnet or VLAN that you're connected to. If you're having difficulties with your discoveries, it's often a good idea to combine host discovery techniques in one shot to get around combinations of firewall filtering methods. At DEF CON 16, the author of Nmap Fyodor gave an example where he showed combining different probes including ICMP echo, aka ping, ICMP timestamp checks, ACScan and SYNAX scans, which looks like this big long command, nmap-sp-pe-pp-ps, and then he used the ports 21, 22, 23, 25, 80, 443, and then he did PA, 80, 443 and so forth, as you can see here. It sounds like a lot to remember, but once you get the hang of it, it's actually not that bad, and you can refer to this video or the man page if you get stuck. So -S is the ping scan. More on scan techniques in a little bit. -PE, that's capital PE, is the ICMP echo discovery, otherwise known as ping. -PP, the two capital P's, is the ICMP timestamp discovery method, and -PS is the SYNAC, effectively a normal TCP handshake discovery. This particular one is telling it to do handshake ports on ports 21, 22, 23, 25, 80 and 443, which is FTP, SSH, Telnet, SMTP, HTTP and HTTPS respectively. -PA, capitals, is the ACK or ACK discovery method, and that's what's going over ports 80 and 443 and 10042. The use of --source-port 53 is to effectively make it appear that the scan is emanating from port 53 TCP, which, by the way, is DNS. And the reason for using DNS is that it's often allowed to traverse firewalls because it's an essential internet service. So you're kind of just saying, hey guys, I'm making the scan, but it kind of looks legitimate because I'm going over a DNS port rather than some other type of port, or just knocking on doors. So it's a little bit more, I guess, finicky. Finally, the -T4, capital T4 flag specifies the timing, and I'll give you a bit more about timing later. That this is an aggressive timing switch, basically meaning that it's going to complete the discovery quicker, which has the downside of being harder on network equipment and probably more likely to be seen by an intrusion detection system. The result of running this discovery, especially across multiple hosts, is a far more comprehensive discovery than with just one type of discovery. FIDO compared a standard discovery probe over 50,000 IP addresses and got a result of 3348 hosts responding as up, and the scan took 27 minutes. When he reran the probe with the extra flags that we've got here, the success rate had increased by 34%, showing 4,473 hosts up. The only drawback, because if you increase the probe types, it also increases the time to run. Instead of the original 27 minutes, it ended up taking 71 minutes. However, many consider that trade-off worthwhile if you're requiring a forensic type of network discovery. Finally, to wrap up the network discovery section, here's an example you can use to combine your learnings so far, but additionally to generate arbitrary lists of random IP addresses to scan if you like. But be warned, if you actually started to scan these machines with the list generated, then you may be breaking the law. So this is just so you can get a summary of the host discovery skills that you've just learned. So try this. Sudo nmap dash lowercase I capital R 25,000 dash lowercase s uppercase L dash n greater than 25k dash ips.txt. If you do that, Nmap will generate a random output of 25,000 IP addresses that are contactable on the internet using its random IP address generation flag, which is the -IR one. The -SL does a list scan, so it doesn't actually run a port scan, just creates a list, and the -N, as we saw before, is to not create a DNS lookup, which obviously if we're looking up 25,000 IP addresses, DNS details, we'd be waiting a very long time. The output of this is then redirected to 25k-ips.txt. You could tidy up this list by doing the following grep command on it, and that will give you a list that you could then input into an Nmap scan at a later time. For example, sudo nmap-ss, lowercase s capital S, dash lowercase I, uppercase L, 25k-ips-sorted.txt. Alright, scan techniques. Nmap has a number of scanning techniques. If you want to run Nmap as a non-administrative user, it will default back to using the standard connect technique, which is analogous of you doing a telnet to the host on the given port number. Nmap has some more stealthy type of scans, and by default, when run as root, it uses a scan type known as a SYN scan, otherwise known as a half-open scan. Just quickly on the theory then, TCP has a way of controlling the information it gets, thus why it's called transmission control. This makes it a very reliable protocol, as opposed to its low overhead brother user datagram protocol, or UDP. When you establish a connection to a host, the client makes a three-way handshake. The process is as follows. Firstly, the client state is set as closed, and the server state is set, as you'd imagine, as listening. And I'll tell you the states as we go through. The client then sends a SYN, or a synchronization request. So the client state has now changed to SYN sent. The server is supposed to respond to say there, hey there, how's it going? I acknowledge your request to synchronize your communications. So the client state is still SYN sent, and the server state is now changed to SYN received. This is called SYN-ACK. If communications are successful, the client should receive the SYN-ACK from the server. So the client state would now be established, and the server state would be SYN received. And then it would send off a final message to say, "Thanks, I understand you received and acknowledged my request to synchronize communications." That final message is an ACK. The client state is still established and the server state is established, both ends saying established. Each of these messages have a sequence or a seq number, SEQ, which are attached to them so that the ordering of the messages don't get messed up in the chain of events. So back to our scan, this stealthy SYN scan type. It's called a half-open scan type because the scanner sends a synchronization request, and if it receives the SYN ACK message from the target, this is a confirmation from that server that it is up and the port is open. Now, rather than doing the usual ACK at that point, NMAP sends an RST, a reset, which aborts the connection, fooling the target into believing that there was an error in the connection, rather than proceeding with the whole TCP packet sequence. In effect, the target is giving away the information that the port is open without actually saying so, and that's why this is a stealthy scan. Modern firewalls and intrusion detection systems are generally aware of this behaviour, so if you are scanning targets which you suspect may have a firewall in front of them which has some sort of smarts, then you should take that into account. Simply throwing hundreds of thousands of SYN scans at a host or a bunch of hosts will likely get picked up by a firewall. At least it will log these events, and at worst it will block your repeated attempts and maybe even alert a SOC or a security operations center that someone is trying to do something a bit cheeky. Think of it like this. Imagine you are the owner of a massive warehouse with dozens of doors that open up for trucks and personnel to come in and out of, some frequently, some infrequently. Each one of these are protected with a lock and a key. But what if one of those people that looks after one of those doors forgets to lock it properly? Then an opportunist burglar comes along and tries each door until he or she finds that one poorly protected door. If you were the warehouse owner and you found out that some little punk was trying every door to find a weakly secured one, you'd probably not be too happy about it. Same can be said for port scanning. Now, along with half-open or SYN scans, NMAP can also do TCP ACK scans, TCP window and TCP MEMON scans for even more elaborate port scanning measures. NMAP even does UDP port scanning with the -s uppercase U flag. So what would we use all of these various scans for? Well, you'd use the TCP ACK scan to do firewall analysis, or if the standard SYN scan isn't working. Let's just say that the target that you are scanning is a server that you are permitted to scan, and you know it's up because it's serving pages on port 443. Yet, when you perform a scan with a scan like a default SYN or a ping scan, it says the port is closed or filtered. This is likely because the firewall in front of the target is capable of spotting tools like NMAP and blocking a SYN. Specifically, if you wanted to map out firewall rule sets, the TCP ACK scan helps you determine whether a firewall is stateful or not and identifies which ports are filtered by the firewall. You can use the TCP ACK method with the -SA flag to discover hosts that are behind stateless firewalls, whereas the SYN scan is effective against stateful firewalls. The TCP window scan is exactly the same as the ACK scan, apart from the fact that it exploits the implementation detail of certain systems to differentiate open ports from closed ones, rather than always showing the unfiltered when the RST packet is returned. You can use the TCP window scan with the -SW flag. The TCP MEMON scan is a cheeky little scan that was dreamed up by a hacker called Uriel Memon in about 1996. So it's pretty old. But he discovered that BSD Unix-derived systems, including Linux, simply drop the packet if the port is open given a specific sequence of packets are sent, and therefore NMAP takes advantage of this to determine open ports on a BSD system. You can use the MEMON scan with the -SM flag. Section 6 is about port ranges. As I mentioned earlier, you can scan host ranges by using a range delimiter such as 192.168.1.1-254. You can also do the same for port numbers with the -p flag. So, for example, sudo nmap-p 22 myhost.com will scan for SSH on port 22 on myhost.com. If you wanted to scan for a range of ports, just do it like this, -p 1-1234. This would scan every port starting at a number 1, scanning all the way through to port 1234 inclusive. You can make more complex ranges by using commas. For example, -p 110, 143, 8000-8080. This range scans port 110, then 143, then the range 8000 through 8080 inclusive. You can even do both UDP and TCP in the same scan. For example, -p, U with a capital, colon 53, comma, T, capital again, colon 53, comma, 1024-8888. This example scans UDP port 53, TCP 53, and then TCP ports 1024 through 8888 inclusive. Finally, you can use the names of services rather than port numbers if you prefer. The names have to match with the relevant services though in the etc services file. For example, -p http, pop3, IMAP4 would give you a scan on HTTP on port 80, pop3 on port 110, and I think IMAP4 is 143. Section 7 covers fingerprinting as well as service and version detection. This is where NMAP goes into overdrive and does stuff that an out-of-box kind of port scanner, the vanilla sort of port scanner tool, would not. And this is where kind of NMAP kind of went for the next level. It can be used to try and detect what version of operating system or service that you are running, even down to the version. So, for example, it is theoretically possible to use NMAP to therefore figure out that a server is running Red Hat Enterprise Linux 8, kernel version 5 with Apache Web Server version 2.4. I say in theory because your mileage will vary depending on how the servers or network equipment have been hardened, if they're configured with their defaults, and often they're configured to reveal much more about themselves than they should. So first off, let's look at fingerprinting or operating system detection. Sudo nmap-O will run a SYN scan and then determine the device type, i.e. a server, and then show you what operating system it is running, i.e. Linux or Windows, etc, etc. And there may be further details regarding the operating system available too. More aggressive scans can be made for further possible accuracy using the --OS scan -guess flag. The maximum number of OS scan tries can be set with --max-OS tries 1. Next up, for service identification and version scanning, you can use the -SV flag, that's lowercase s, uppercase v. This is very powerful because it can tell you the version of a particular service. So for example, you say you have scanned a server and it's open on port 80, or you can say that it's likely to be a web server. If you knew which version of web server it was, then you could be able to ascertain whether the version of the web server is vulnerable to attack or not. So let's do sudo nmap-sv-p80 webserver.com. A response with 80/tcp open http Apache HTTP 2.4.4 brackets Ubuntu would mean that the webserver.com target is running the Apache web server product. Specifically, it's running an old version 2.44 and it is running on an Ubuntu Linux server. There's plenty of information for you to go over, like cve.org or somewhere similar, and type in Apache 2.44 to see if it has any known vulnerabilities that could be exploited. So this gives you a really strong bit of recon. A few other flags can be added to an SV to nuance the version scan. For example, --version -intensity is a number from 0 to 9. A higher number increases the possibility of correctness, but it is more obvious in the scan. so it will get picked up easier by intrusion detection systems. There's also a version -light, which is less likely to be correct, however it is faster at scanning. For a trifecta of OS detection, a version detection, script scanning and traceroute in one scan, use the -A flag. Section 7 is about evasion techniques and timing. Obviously, when you're scanning a network or even just a host, it is highly likely that it will be picked up by an intrusion detection system of some type at some point if you keep on doing it. NMAP has timing-based evasion techniques built in that handle this. Obviously, this can lead to some pretty dramatic slowdown of scans, so that it is a trade-off that you must make to avoid detection in some cases. The -T switch alters the timing depending on what level of paranoia you want to assert. -T0 provides the most paranoid level of evasion, T1 provides sneaky mode evasion, T2 is called polite mode. It slows down the scan to use less bandwidth and less resources on the target host. T3 is the normal default speed setting, T4 is an aggressive speed scan which assumes you're on a fast network, and T5 is the insane speed scan. It assumes that you're on a top tier network which is fast and has lots of bandwidth. It is of course the most obvious to the target that it's being scanned because it is basically flooding it with packets. So use that carefully. There are some other tweaks that you can make to the timing that can help either speed things up or make detection harder. These are -min-rate 50. This will send no slower than 50 packets per second, or -max-rate 50. This will send no more than 50 packets per second. Outside of timing, you can evade firewalls and intrusion detection systems by using a series of other options. Here are a few examples. -f, for example, uses tiny fragmented IP packets. This is hard for packet filters to pick up and deal with. -G or --source-port 53, as demonstrated earlier in this video, you can spoof the port at which you appear to be connecting from, making it look like you're making a legitimate request. The example here is port 53, which is DNS, which is a server which is often treated with a better level of trust by a firewall. -D and then a list of hosts sends the scans to appear as if they were coming from these spoofed IP addresses or host names. So, for example, you could do -D myFakeIP1, myFakeIP2, and then on to the target host. -S and then the list of hosts again would this time spoof your client's host name to be that of something else. For example, nmap-S pornhub.com target host. That would make the targethost.com believe that you're coming from pornhub.com. Just don't forget to tack on a scan of -P69. -proxies will then allow you to send all your scans through a particular given HTTP or SOCKS4 proxy rather than coming directly from you. -data-length. This appends random data into the packets, basically obfuscating the content of them to the eyes of an IDS or an IPS. The number that you choose specifies the amount of bytes to append to the packet. Station X have a great NMAP cheat sheet available, which I will link to in the description. They give an example IDS evasion command which combines many of these approaches. nmap-T0-N-P lowercase n -data-length 200 -D 192.168.1.101, 192.168.1.102, 192.168.1.103, 192.168.1.23 targethost.com. So breaking this down, that means NMAP will perform a scan with tiny IP packet fragments -F, use paranoid intrusion detection system evasion timing T0, not to do DNS resolution -N, disable host discovery, that's PN, set a random data bit of data into the packet of 200 bytes --data length 200, appear as if the scan is coming from the other IP addresses, the spoof. This will spoof from 192.168.101, 102, 103, and 192.168.1.23, and the target, of course, is targethost.com. Section 8. Output Options. NMAP provides nice output as it is. Visually, it's clear to the eye about what the results are when a scan or a network discovery is executed. However, sometimes you need the output to suit other uses. For example, you might do a scan and you want to find out what all the open ports are on a scan only, and then run some sort of automated process against those open ports to see if they are vulnerable to a given attack. The default visual friendly output of NMAP is not great for this, and therefore there are a number of output options that NMAP offers to solve this problem. The normal output is -o uppercase n. However, you can also dump the results in XML format with -ox, great for API programming, linting, and many other things. Myself, I often use the OG option, not just because I'm the original gangster, but because it provides some greppable output. This can be worked on in so many ways with a Linux shell script. As a rudimentary example, you could do nmap p22 og 192.168.1.1-254 grep22/open. This would provide a result like this. That sort of output makes it super easy for me to grab just the details I want. For example, nmap-p22-og localhost, then I could pipe that into awk and then do a /22//open/print in braces $2, which would simply provide the result I need, which is the IP addresses. The -OA flag, that's capital A, would output to all three methods at once. The --append output appends a scan to a previous scan file, and also -v or VV increases the verbosity, and D or DD increases debugging. Section 9. Taking it to the next level. NSE. This is the final section of this video, where we talk about NSE, NMAP's scripting engine. All of the stuff that we've talked about so far is plenty to elevate you from someone with conceptual knowledge to practical knowledge when it comes to port sniffing and host discovery techniques. The card that NMAP has up its sleeve when it gets set apart is NSE. NMAP comes with its own scripting language, as well as a bunch of built-in scripts that can be used to easily extend the capabilities of NMAP. On top of this, you can write your own SE scripts, so you can combine tools and techniques to quickly get your job done. For example, it has the capacity to exploit vulnerabilities, not just detect them. I'll only touch on a few of the highlights here to get you started, but it's well worth looking into. More information can be found in the link in the description. The scripting language that is used for NSE is the popular Lua scripting language, version 5.3. Firstly, NSE is invoked with the -lowercase-s-uppercase-c option, or --script, if you wish to specify a custom set of scripts. It is important to note that the outputs currently only output to the NMAP normal output and XML outputs. This option is considered safe for most scans. --script default, this option scans the default script options. It's also safe and very useful for general discovery options. --script equals banner. This option will show you the banner from all the ports that are open. For example, when you connect to an FTP server, it often shows you what type of FTP server you're connecting to and what version number it's running. For example, I am running an FTP server on my Raspberry Pi at home, and NMAP shows this: 21/TCP open FTP banner : 220 VSFTP D 3.03. So not only do I now know that FTP is open on that server, I can also tell that version 3.03 of the VSFTPD product is running. Another example is --script equals HTTP star, which means scanning running using a wildcard script search. That means it will execute every script prefixed with HTTP. You can combine multiple scripts like this as well. --script equals HTTP star, banner. That would run all of the HTTP scripts and the banner script at the same time. You can scan using the default scripts, but remove the intrusive ones by using not intrusive, e.g. nmap target -- script not intrusive -- script -args provides arguments to any given script. For example, sudo nmap -- script snnp -sysdesker -- script -args snnp community equals admin cisco router.local. This would run the snnp system description script against the host known as cisco router.local and provide the login for the snnp community variable to be admin. Well, that's about all we have time for. I hope you've enjoyed it and learned something new. Until next time, thanks so much for watching. Have a good one.